The world population is currently quelling around 80% of its hunger for energy with oil, coal and gas. If this situation does not change, we will have to suppress our appetite in future because the fossil fuel reserves will not last forever and their consumption involves the release of the greenhouse gas carbon dioxide. In order to continue to sustainably supply humankind with energy in the future, completely new energy sources must be tapped and technologies that are more friendly to the environment must be developed. Research Center Jülich, a member of the Helmholtz Association, has taken on these challenges. With its targeted energy research, Jülich is aiming to develop strategies to meet the future demand for energy in a sustainable, safe and environmentally friendly manner. At the Institute for Plasma Physics, for example, scientists are working towards using the fusion of light atomic nuclei to generate energy. In a few decades, nuclear fusion, together with renewable energies, will be available as a new primary energy source and will make a substantial contribution to finding a solution to the energy problem. Fusion researchers have already demonstrated in international corporations that they understand and can control the physical principles for igniting the fusion fire. Now, with the participation of scientists from Jülich, it must be shown that economic, continuous operation on a power plant scale is possible. Nuclear fusion. This is the reaction between the raw materials deuterium and tritium. The fusion of these two hydrogen isotopes produces the largest amount of energy compared to all other conceivable reactions between light atomic nuclei. The deuterium-tritium reaction takes place according to the following principle. The two atomic nuclei fuse to form a helium nucleus, and additionally, they set free a neutron. This causes a large amount of energy to be generated, which is contained within the high velocity of the escaping neutron. A chain reaction is basically impossible. The deuterium-tritium reaction is fully controlled and can be ended at any time should this be necessary. This is the overwhelming safety advantage of nuclear fusion, along with the fact that its end products are not radioactive. Tritium, which is super-heavy hydrogen, is a weak radioactive emitter with a relatively short half-time of only around 12 years. For this reason, by far not enough natural tritium is available on Earth to suffice for fusion power plants, only about 2.5 to 3 kilograms worldwide. Tritium, therefore, must be produced artificially, by bombarding lithium, the lightest alkali metal, with neutrons. As well as the desired tritium, the harmless noble gas helium is also produced here, as in the deuterium-tritium reaction. Thus, the actual raw materials for nuclear fusion are deuterium and lithium. Lithium is a readily available raw material that can be found, for example, in large quantities in natural rock everywhere on Earth. As a raw material, deuterium is just as easily obtained and can be extracted from normal water all over the world. Moreover, nuclear fusion is exceptionally lucrative. As little as 2 liters of water and 250 grams of rock are enough to cover a European family's demand for electrical energy for an entire year. An important step towards a fusion power plant is the worldwide effort which has seen construction begin on the ITER experimental reactor in Europe, or to be more exact, in Cadarache, in the south of France. ITER is a Latin word and means the way. Together with scientists from China, India, Japan, Russia, South Korea and the United States, and the whole of Europe, physicists, technicians and engineers from Research Center Jülich are working intensively on the construction of ITER. Their shared goal is to harness the energy production mechanism used by the Sun and other stars for safe and controlled use on Earth, and thus ensure that enough energy will still be available for future generations.
With ITER, we will realize for the first time in worldwide cooperation a burning fusion plasma. With this 500 million watt fusion plasma, a burn duration of at least 8 minutes and the test of new technologies, we will contribute to the design of the first real fusion power plant. with which we expect to feed electricity from nuclear fusion into the grid approximately by the year 2035. Our work in Jülich, addressing the interaction of the 100 million degrees hot fusion plasma with the walls, and our know-how in plasma physics and fusion technology will contribute to the success of ITER.
Using what is known as the tokamak principle, nuclear fusion can be put into practice on Earth. The Russian abbreviation tokamak stands for a toroidal chamber with magnetic coils. The tokamak was invented in the 1960s in Moscow. Even today, it remains the most successful strategy for using nuclear fusion to generate energy on a power plant scale. The gas mixture of deuterium and tritium is let into the toroidal vacuum chamber that simultaneously represents the secondary winding of a large transformer. Many millions of amperes of electrical current combined with the other heating methods turn the gas into a plasma with a temperature of 100 million degrees. Plasma is the mixture of free electrons and ionized atomic nuclei, which is just what is needed for the fusion of deuterium and tritium. Strong magnet coils create an invisible cage that prevents the plasma from coming into direct contact with the surrounding walls of the burn chamber. The European Union has set itself the goal of constructing the first fusion power plant by 2035, which will be capable of feeding electricity into the grid. The Jülich research program plays an important and steady role in these endeavors. TechStor, the research center's fusion experiment, is being used as a testing and developing environment for the realization of this goal. An important area of expertise in Jülich is the interaction between the fusion plasma, which is many millions of degrees hot, with the walls of the surrounding burn chamber. Inside TechStor, materials that can withstand this immense thermal load, graphite and tungsten, developed and tested in Jülich, are being designed to line the walls of the ITER burn chamber, which measures 680 square meters. To continuously operate a fusion reactor, the wall components must have a long lifetime under high loads, and stationary and stable plasma confinement must be mastered and controlled under every condition imaginable. The control room. From here, TechStor is operated with the aid of the most modern computer technology. During plasma experiments, you will find physicists, engineers and technicians here. Results appear as quick as lightning on the computer screen, where they are evaluated. Conclusions are immediately drawn from these for the next experiment. Many young scientists are completing their PhD or master's thesis on TechStor. Neighboring universities from North Rhine-Westphalia, Belgium and the Netherlands are also heavily involved here. International visiting scientists are an everyday sight. In particular, colleagues from the Netherlands and Belgium, who in conjunction with Research Center Jülich founded the Trilateral Euregio Cluster and who operate TechStor jointly. The catchphrase, often used by plasma physicists, "waiting for the shot," applies to the next experiment in TechStor, the production of fusion matter that is millions of degrees hot. Another area of expertise at Research Center Jülich is the development and testing of systems that can be used to measure the properties of the fusion matter, for example temperatures, densities, magnetic fields and impurities in the plasma. Here, for example, a measuring system known as a spectrometer is being developed for the analysis of extremely short wavelength ultraviolet radiation for use at the ITER International Fusion Reactor and at the Greifswald Stellarator Wendelstein 7X. This measuring system is indispensable for the operation of future fusion reactors and will be initially tested at TechStor in Jülich. International cooperations are central to fusion research. Presentations and meetings beyond borders, particularly in conjunction with European partner institutes, aid the exchange of knowledge and the planning of joint experiments at TechStor and other facilities. This is how, together with researchers from all over the world, The Institute for Plasma Physics at Research Center Jülich is developing solutions and concepts for the construction of nuclear fusion power plants which will ensure a safe, resource-conserving, environmentally friendly power supply for future generations.